Okay, so this lesson is going to focus on the cross product for vectors. So we've learned already with the dot product that represents scalar multiplication. So when you do the dot product between two vectors, you end up with a scalar. Well, now we're going to do something called the cross product, which means we're taking two vectors, multiplying them, and ending up with a new vector. So the word cross literally means cross product, which we'll see in a little bit more detail later. But this x doesn't mean we're just going to multiply the numbers together. We actually have to do the cross. And the dot, for dot product, tells us that it's the dot product. Now, the cross product is only defined in tree space. So that's really, really, really important. Because what we're doing when we're finding the cross product is we are generating a vector that's perpendicular to two vectors at the same time. So here's a little diagram so you can see what's happening. So here the vector of the cross product. So I have vector A and I have vector B. When I cross them, you'll notice down at the bottom that the angle between them is 180 degrees. So if I move it to the right, I'm making the vector. You'll notice the vector that's greater than 180 degrees, that new vector C is pointing downwards. Now if I keep sliding, I'm back to 180. So then I go here, you'll notice the vector is growing upwards. So that vector C is perpendicular to both A and B at the same time. So anytime you're finding the cross product, that is your ultimate goal in terms of what's happening. Now for us, those vectors are either going to come out of the page or into the page, or for me at the smartboard, out of the board or into the board. Okay, so this is the formula for geometric vectors. So remember, geometric vectors are given to us with specific angles. They're not coordinates. So A cross B, right? Again, we got that cross B is going to be the magnitude of A times the magnitude of B sine of theta. So by finding that sine of theta, we're finding the vector that's going to be perpendicular to both of these vectors here. Now, when we are looking at this, we have to figure out, is it going to be going up or is it going to be going down? So in this case, because I'm doing A cross B, I'm going to take my right hand and I'm going to point my fingers along vector A and curl towards B. The only way that I can get that to work is for my thumb to be pointing upwards. If I were to do it in the opposite direction, where I had B cross A, so if you put your fingers along B and try and curl towards A, you can't do it so that your thumb is sticking up. Your thumb has to be sticking down. When I'm back in front of you, I'll go over this a little bit more in terms of what's happening. But there's only two possible directions, either out of the screen or into the screen, or out of your page or into your page, because that's the only way that one vector can be perpendicular to the other two. Okay? Okay, so now here there's a bunch of different applications of the right-hand rule. So there's angular velocity, which I think some of you have learned about, torque and force, which we'll go over a little bit more. It's also used when we're talking about chirality in molecules. So I know a lot of you are doing chemistry right now. So chirality has to do with isomers. So they're mirror images of each other. Exact same chemical formula, exact same chemical functional groups. However, they're not, it's like a pair of gloves. So the fact that they're not mirror images, that's why we call them chiral. So that'll have something to do in terms of the right-hand rule. That's something that you can investigate on your own a little bit more. But I'm going to show you this little video. Oops. Okay. Okay, so that was a little summary video so you could kind of see how to use the right-hand rule. Now let's actually go and look at some questions. So it's telling me if the magnitude of vector u and the magnitude of v is 20 degrees and the angle between them is 40, they're both in the same plane, find u cross v. So in order to do that, on the previous slide, it told us that our cross product is equal to the magnitude of u times the magnitude of v times sine theta n hat. So for this one right here, when we're looking at it, if I do a little sketch, the angle between them is 40 degrees. So I have 30 multiplied by 20 times the sine of 40 degrees n hat. So I'm saying that this here is u and this is v. So this is really important for describing what's going to happen next. So this becomes 38.6 n hat. And based on my diagram, this would be out of the screen. This one here, v cross u, so instead of starting with u and crossing towards v, I'm going to start at v and go towards u. I'm going to have the exact same magnitude, but this time the direction is different. So it's like I have the red line, so my red calculation, the first one, would be like this. The second calculation would be, oops, like this. So we're going to pretend that that's straight. Okay. All right. Now, fortunately for us, we use Cartesian or algebraic vectors a lot more. So in order to do that, we have a formula for the cross product. So you'll see that you can memorize this formula if you want to. However, I'm not one for memorizing. I like to know a process so that it'll always work. So you'll notice when we're finding the x component of the cross product, we're not actually using the x components at all. It's built from y and z. Now the reason why this needs to be memorized or developed is because of the minus. As soon as we have subtractions, that means that order matters. So when we're doing the x and y components, or the y and z, or the z and x, there's two different formulas we can use, and it's just how you orient them. So anytime you want to do the cross product of two algebraic vectors, you are going to take the vectors and you're going to write them. So we have ax, ay, az. So I'm going to write them twice. Ax, ay, az. Now my second vector will be bx, by, bz, by, bz. So these will be numbers. From here, you're going to cross off the top two lines, or sorry, the top line and the bottom line. So that means my x component, you're literally going to cross. So you have a y times b z minus, now I'm going to cross this way, a z times by. So that's my x component. My y component, now I'm going to do the next pairing. So I'm going to have a z bx minus ax bz. The z component will be the last three, or not last three, but the last two. So ax by minus ay bx. Okay, so then each of those values, when you actually work them out, will give you the value of your cross product. The other way that you can write it is, instead of doing it vertically, you could write it horizontally. So I'm just going to separate that here. So you would have ax, ay, bz, ax, by, bz, bx, by, bz, bx, by, bz. So I'm just rewriting it. So again, I'm going to get rid of these two. So when I work that out, my x component is going to be the exact same thing I got on the other side. It's just some people like looking at it visually this way. Minus by, bz, or not by, sorry. Or did I make a mistake? I made a mistake right here. So there should be az, which means this is az right here. Then the y component will be az bx minus bz ax. Again, you'll notice there's no z component included. No y component when we're finding the y component. And then the third value that we're going to have will be our z component, which will be ax by minus bx ay. So that's a lot of letters. Now let's actually do an example. So we have these three vectors, and I'm asking you to find A cross B. So once again, the order matters because of the direction. So I'm going to write vector A twice. I like the vertical one better, but that's just me personally. So then I have 4, 3, 6, 4, 3, 6. I'm going to cross these off. So when I'm doing this cross product right here, so A cross B is going to equal. So I'm going to have 1 multiplied by 6, so I'm going to have 6 minus negative 6. Because the minus is part of the equation, and negative 2 times 3 is negative 6. Negative 2 times 4 will be negative 8. And then I'm going to have minus 42. And then 7 multiplied by 3 is 21 minus 4. So this becomes 12, negative 50, 17. So when I do the cross product of these two vectors, this vector right here will be perpendicular to both of them at the exact same time. Okay. Now down here, determine A cross B plus C and A cross B plus A cross C. What do you notice? Okay, so first of all, when I look at these equations right now, when I'm looking at them, it looks like I've distributed the A cross B into the bracket. And that is basically that property that I'm going to prove that you're allowed to do. Okay, so this first one right here, A cross B plus C, where I do the B plus C first. So 7, 1, negative 2, cross B plus C. When I add those vectors together, I'm going to get 3, 5, and 10. When I do this cross product, I'm going to get 10 plus 10 for my x component. So I'm doing this on the side with the cross product. So I have negative 6 minus 70, and then I'll have 35 minus 3. So that's going to give me 20, negative 76, 32. So that was this right here. Now, if I do the other part where I do A cross B and A cross C, so I already did A cross B above, and I got 12, negative 50, and 17. So I'm going to add 7, 1, negative 2, cross with negative 1, 2, and 4. So this becomes, and if you take the time to actually do the cross product, you're going to find that this here is 8, negative 26, and 15. So it shouldn't be too surprising that these two things are the same. Because this here, when we look at our properties of cross product, is this property right here. Okay, Okay, now this thing here, it's not a negative, it's a star, like a bullet point. So what they say, if you have two vectors u and v and even w and some scalar k, these things will always apply. U cross v is the same as the negative of v cross u. So that should make sense, because as you saw in one of the examples, if you do u cross v, it's going to be pointing upwards, and then the negative would be pointing downwards. So it's simply a directional thing. Here, the u cross v distributes in, but you maintain the cross. So it becomes u cross v times u cross w. Finally, if u and v are non-zero, u cross v will equal 0 if and only if they're scalar multiples of each other. So if you were to do this proof, if the vectors are scalar multiples of each other and you do the cross product, you're going to get 0 because it's the same vector, it's just on top of itself. So if you think about it, the sign of 0 has a value of 0. You end up with an overall value of 0. So this is just giving the proof portion down here. Whoops, way too liberal with that marker. Okay, you get the idea. All right, so that concludes the lesson on cross product. So hopefully it all makes sense.